In part 2 of this video on the dot product, we're now going to look at the Cartesian form of the dot product. When you're working with vectors that are in Cartesian form, then we're going to need a different formula than the one we had before. What we did in the first video was very much tailored to having vectors in polar representation, where we had their lengths and their angles. If they're in Cartesian form, you could convert them back to polar, but this converting to and from, back and forth between polar and Cartesian leads to round-off errors. It better is to actually develop the form that we can use. It is quite easy to take the dot product of vectors in Cartesian form, provided you know the formula. Let's say that we had a vector A with an x component I hat, a y component j hat, and a z component k hat. And we had another vector likewise with components bx I hat, by j hat, bz k hat. The dot product of those two vectors is very simple. You simply take the x part, ax, bx, and multiply them together, and then you add the product of their y parts, and then add the product of their z parts. And if in fact the vector had more dimensions, there is no reason that you have to make them just be like space and only have 3. You could continue this on to the q hat, aq, bq, ap, bp, and whatever other dimension you wanted. So as you can see, if you have these numbers ax, bx, ay, by, az, bz, it's going to be easy to multiply the numbers together to get a scalar and then add up the 3 scalar numbers. Now, we'll show you that this is actually true. This is certainly a formula that you want to put to memory. And the proof is not very hard. It's basically just from algebra class. So here's what we're going to do. We write a dot b is ax I hat, ay j hat, az k hat, dotted with bx I hat, by j hat, bz. This is like x, y, and z. And this is being multiplied by something like a, b, and c. So you take the ax I hat, and you dot it with the first term in the second vector. Okay, so a dot b would be ax bx I hat dot I hat. Just taking the first term and dotting it with the second. Now here's the thing. The dot product order of the unit vectors doesn't matter. You can switch them. And these b's and a's, they're scalar numbers, so they can come past the dot. So I pulled the bx out front. Now I'm going to take the first term and I'm going to multiply it by the second term. So plus ax by I dot j. And then I'm going to do it with the third term. ax bz I dot k. And then we'll have more terms. Now if you see, the first term on each one of these had ax, and the other terms had the components of the b vector. So next time on this row I'm going to do the y, starting with ay bx. That would be j hat dot I hat, and then ay by j hat dot j hat, and then ay bz j hat dot k hat. All right, done 2. Now we need to do the third. We're going to take this term plus az bx k hat dot I hat plus az by k hat dot j hat and az bz k hat dot k hat. Nothing really hard, but kind of tedious to have to write out 9 terms, 3 times 3. Now, what we need to do here is to look at these dot products. So let me draw you a little picture of these guys. Remember, I hat is a vector of length 1, and we're dotting that, in this case, with I hat. So I hat dot I hat. We can use what we learned in the last video. This is the length of the first, which is 1, times the length of the second, times the cosine of the angle between, but the angle is 0. The cosine of 0 is 1. So it's 1 times 1 times 1, which is simply 1. On the other hand, if the vectors are different, like I hat and j hat, then the angle here is 90 degrees. So we have I hat dot j hat is 1 times the cosine of 90. But the cosine of 90 is 0. That's because these vectors are perpendicular. So this term goes away, 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 this term goes away. And this term becomes 1, and this term becomes 1. Notice the only terms that remain are along this diagonal on the inside. Hence the name sometimes the inner product. And what do we get? We have AX, BX, AY, BY, and AZ, BZ. Exactly what I wrote before. So A dot B is AX, BX, plus AY, BY, that's the second term, and the third term, AZ, BZ, and all the other terms, because of these dot products, go to 0, because the unit vectors are perpendicular to each other. Let's do some numbers. Let's say you're given the following. A is 3 plus 2i, B is minus 4 plus 3j. Find the dot product. Well, A dot B is the x part of A, 3, times the x part of of B, minus 4, plus the y part of A, 2, times the y part of B, 3. So minus 12 plus 6 is simply minus 6. It is easy to take the dot product when you have something in Cartesian form. Don't even need a calculator most times. Don't need any trig functions. Now, the dot product has many applications. One of its most useful one is finding the length of a vector, the vector's magnitude. If you're looking for the length of a vector, also could be said to be the absolute value of the vector, then what you do is take the square root of the vector dotted into itself. Now, why is this? Well, A dot A is the length of the first vector A times the length of the second vector, which is still A, times the cosine of the angle, which is 0, but the cosine of 0 is 1. So that's just the length squared. So A is the square root of the vector dotted with itself. Something interesting. Let's look at it from Cartesian land. Well, in that case, A is the square root of ax squared, because ax times ax is ax squared, plus ay squared. And if you only had 2 dimensions, you've just found the Pythagorean theorem, a special case of the dot product. But if it's 3 dimensions, you get the 3-dimensional Pythagorean theorem. Oops, sorry, put the wrong squared. So you simply take each component, square it, add the components together, and take the square root. Let's show you how that works on one of these. What is the magnitude of the vector who's got a length of 2i, 3j, minus 4k? What are we looking at? We're looking at something, if this is x, this is y, and this is z. This thing goes back out 2 units. it goes over this will weigh 3 units, and then it drops back down like this. So it's down underneath this curve. To find B, you simply take the square root of -2 squared plus 3 squared plus -4 squared. B is the square root of 4 plus 9 plus 16. So B is the square root of 29. And that's how you find the length of any vector. And we'll pick this up in the next video with some more ideas about using the dot product.